Hello, we are COTAN Engineering. Our team consists of Alejandro Soriano, Hydraulics and Structural Engineer, Tyler Enderwish, Project Manager and Geotechnical Engineer, Nicholas Avlani, Traffic and Construction Engineer, Carlos Gill, Hydraulics and Quality Control Engineer, and Alexis Armijo, Environmental Engineer.
The San Diego Pure Water Program is a drought-proof, locally controlled water supply designed to reduce imports of water income from Northern California and the Colorado River. The Pure Water Program proposes water recycling to provide the city with sufficient technology in order to provide a third of San Diego usage of water by 2035. One of the major components of the San Diego Pure Water Program is the Morena Pump Station Facility and Force Main, which will provide sewer water from the pump station facility to the North County Water Purification Facility. COTAN Engineering is pleased to present the design for this task. The Morena Pump Station Facility is located in 887 Sherman Street, and the pump station gathers influent sewer from the east side of the facility, and the pressurized sewer exits on the northern side of the facility. The force main consists of a 48-inch discharge line that will bring sewer water into the North City Water Reclamation Plant. In order to justify our selection of the alignment, COTAN Engineering developed a grading scale to choose the most appropriate selection. 3 alternatives were analyzed based on their compliance to the environment, traffic, cost, and constructability. Alignment 1 was selected since it got the greatest score. This alignment traverses along the following streets: Sherman Street, West Morena Boulevard, Claremont Drive, Genesee Avenue, Noble Drive, into the North City Water Reclamation Plant.
As the title of the project says, a sewage pump station and pipeline need to be designed, and wastewater totally constrains the decisions made. The main objectives go through finding the optimum combination of pipe and pumps under the duty points of 30 MGD and 7 MGD, defining and sizing the wet facilities involved, such as the pump station or the screening facility, and selecting valves and other appurtenances appropriate for sewage. In order to find the appropriate pipe size, system curves are developed to find the pumping requirements, and pumps are selected. Equivalent annual cost of investment are calculated under expected economic conditions, and a 48-inch pipeline is found to be the most cost-effective, what involves a total dynamic head of 485 feet. Under the existing conditions, 5 corner pumps are selected for the reliability under the design flow of 30 MGD. The total installed power around the 3200 kilowatts. The pump station is designed with a wet well, dry well configuration. The pumps are installed in the dry well, whereas the wastewater is suckled by the suction pipes from the wet well. Screen devices are also necessary to be installed, so solids large but the pumps can handle cannot enter them. As this is the reason of a lot of maintenance tasks, a separate facility is designed to facilitate its success. In addition to the pipe and pumps, several other elements are necessary for the correct running of the system. Inside the pump station, isolation valves are installed to make possible the dismantling of the main elements. Furthermore, pump control valves are located on the discharge side so slow openings and closings can be accomplished, thus avoiding transient surges. Their typology is wedge gate and eccentric plug respectively, that are found satisfactory for wastewater. Around the alignment, it is necessary to install isolation valves too, to separate sections of the pipe. Air combination valves are necessary at the high points and at constant slopes, so column separation is avoided. This is a transient mitigation measure and allows vacuum relief or pressure release accordingly.
The tasks involved with developing a project of this magnitude rely heavily on the geological and geotechnical aspects of the proposed site. For this reason, our goal was to identify potential geotechnical issues and constraints that could impact the feasibility of this project. From a geotechnical aspect, the pump station site subsurface is of major concern since this will be a large component of the project. Being that the pump station site is located along the San Diego embayment basin, all design considerations are under the assumption that the soils encountered consist of uniform alluvial deposits ranging from loose to medium dense sands. Additionally, based off the elevation of the pump station site and its location relative to the river basin, all design considerations are under the assumption that the groundwater table is 5 feet below existing ground surface. Using these assumptions, we are able to determine fundamental geotechnical design aspects such as allowable bearing capacity, settlement, consolidation, and the pump station site's susceptibility to liquefaction in the case of a seismic event. One of the most important design considerations is to analyze the induced earth pressures at the pump station site because of the deep excavations up to 30 feet. In addition to design considerations, there are several geotechnical construction issues that need to be assessed. A combination of deep excavations and a shallow water table drives the need to determine if heaving, also known as static liquefaction or boiling, will be an issue. Furthermore, it is necessary to analyze the groundwater flow into the excavation in order to determine the uplift pressures on the foundation so that it can be designed accordingly. Perhaps the most critical construction issue that needed to be addressed was the dewatering of the excavation. For our design, a system of double-sided shallow well points are used to lower the water table at the site to assure a dry excavation for construction purposes. Finally, based on the alignment selection, there are 4 areas where open excavation to place pipe is simply impractical. As a result, trenchless excavation techniques are needed to be implemented. There are a few methods that can be used to accomplish this, and based on the pipe material, the size, the geological conditions, the most suitable option is the jack and bore method.
Structurally wise, this project takes care of the integrity of all the buildings built. There are several constraints, most of which are found in the pump station building that is the most delicate. Generally speaking, the objectives are to resist load supply, such as soil pressures, hydrostatic or seismic, ensuring perviousness of the structures provided, and minimize differential settlements. Concrete is chosen as the main construction material here, since it is capable to meet the previous. On the pump station building, it is interesting to point out the use of a mud foundation. This provides rigidity to the building and a solid base over which all the piping can be installed. Furthermore, due to geological conditions of the site, it ensures a better behavior against detrimental events such as heave or liquefaction under seismic conditions.
Construction and traffic go hand in hand with determining the feasibility of the pump station and pipeline projects. Construction deals with many parts including contract packaging, scheduling, and cost estimation. The Morena Pump Station and Pipeline is a design bid build project with up to 6 individual contracts covering things like design, project management, pump station construction, and we estimate 2 to 3 contracts for the force main, including jack and bore activities. This packaging is our assumption and may change as the project management team deems necessary. A general construction schedule shows the overall time frame for the major construction projects. Activities that define the critical path on this schedule are assumed to be a part of the force main construction. This assumption is based on long lead times for pipe segments and restricted construction time space due to this project being built in the right-of-way. Costs are another important aspect of construction. Construction costs are estimated to total around $170 million 2016 dollars, including all contingencies. These estimations were made using the 2009 unit costs from the City of San Diego, which were then adjusted to the 2016 prices. Traffic analysis for this project is important since the force main is constructed within the public right-of-way. The traffic analysis used 2013 average annual daily traffic volume data provided by SANDAG. These volumes generate current LOS scores for segments, which then aid in recommendations for work time and zone dimensions. The analysis also identified traffic directional flows within intersections and made recommendations for night work to reduce traffic impact. Finally, the analysis identified community impacted businesses, bus routes, and schools.
Permits along the force main alignment are needed to ensure that the project construction is being documented, environmentally friendly, and legal. The permits were divided into 3 different categories based on how the permit will influence the scheduling of the project. Categories are high priority, medium priority, and low priority. The high priority permits are the following: the Caltrans encroachment permit, the Section 404 permit, Section 401 permit, Section 10 of the Endangered Species Act, and the railway right of entry by the San Diego Metropolitan Transit System. The medium priority permits were selected. The following are the medium priority permits: the traffic control permit, the construction general permit, and the jet fuel line by the Naval Supply System Command. The low priority permits were selected as the following: the temporary bus route interruptions by the San Diego Metropolitan Transit System, the Development Service Department street resurfacing, and the Development Service Department ADA compliance.
Due to the raw nature of the wastewater being pumped, hydrogen sulfide is present, which reacts with oxygen to form sulfuric acid. It is imperative to ensure conditions at the pump station and in the force main do not promote corrosive activity. A well-designed odor control system will properly handle malodorous gases, thus minimizing any detrimental effects. For the Morena pump station and pipeline, the odor control system contains vapor phase and liquid phase technologies. At the pump station, the vapor phase technologies include a ventilation system coupled with activated carbon canisters. For the force main, liquid phase technologies include activated carbon canisters, injection of ferrous chloride, and air and vacuum valves. In terms of stormwater management, COTAN engineering will protect water quality by preserving and mimicking natural hydrologic functions. This is accomplished through the use of infiltration and filtration integrated management practices, or IMPs. Bioretention areas are shallow depressions of conditioned soils that are planted with vegetation that retain, treat, and infiltrate rainwater. However, due to the proximity of the water table to the ground surface, soil conditions do not promote infiltration. Therefore, infiltration IMPs such as bioretention basins and swales are not appropriate. Luckily, most infiltration IMPs can be modified with an underdrain or liner to provide filtration. For the Morena pump station, the most appropriate form of filtration IMPs is a flow-through planter, which contains soil media and vegetation with an underdrain. The soil media in the flow-through planter provides treatment primarily through filtration, but also through biological uptake and absorption.